Alright, welcome back again. So this is the Chipmaster, and in this video I'll do another repair on a MacBook, right? And the tech told me that it's not turning on, right? So I'm going to see if I can repair it. It's pretty nice and clean, right? It's a MacBook A2289. You know my style. I always like to show you exactly what I'm doing. Can I get a focus? It's trying. Alright, it's not focusing today. It's not focusing. Let's see. Alright, so let me head over the site and see if it can focus. Alright, so as you can see, it's an it's an A2289, and the fault is that it's not turning on. So I'm going to connect the power. Okay, so alright, so I now connect the power to the unit. Alright, so as you can see, I got 5 volts. So I got 5 volts and that's it. It's not boosting. No current draw, as you can see on the DC power supply. I'm just getting like 15 milliamp thereabout. Alright, let me try the other port. Nothing. It's not boosting to 20 volts. Alright, let me try the other side. Oh, it only has 2 ports. Sorry, I forgot. Alright, so I'm going to take it apart. I will disassemble. Alright, this part is a bit tight. Alright, so A2289, A2159 they both use the 2nd gen T2, right? And it's always under this metal here for the T2 and the PMU IC. Alright, first of all, I'm going to check all the areas here for any liquid spill, any explosion, or any form of corrosion that can lead to the clue of the problem. Alright, this is CD3217. Alright, and this is the power delivery chip, CD3217B12, right? And these are the NANDs, right? The NAND power supply here, PP 2.5 volts, all is well. Right down here, which is the common point, and this is the charging section here. No problem there. In the CPU power supply area here, none of the I don't see any burn on any of the DR MOS. Right, there are no burn on any of the DR MOS. All right. And here we have all is well over this side. All right, so I'm going to finish take out the board now and see what I get on the other side. All right, so I'll remove the battery first. All right, the board is out. Also take the port at the same time because I will need it. All right, so on the other side, right here's the second PMU power delivery chip. Sorry. All right, so this is also good. No burn, any explosion, no liquid damage. This is the backlight section here. Right. This is the backlight section here. All is well. The Wi-Fi, all is well. And this is the other two NANDs. All is well. No liquid spill, any burn. Under the CPU here, all is well also. All is well on this side. All the amplifier section is good. I'm not seeing any form of liquid corrosion or explosion or any form of debris on the board. Alright, so I'm going to connect the power supply port DC jack, or type C port rather you can call it. Okay. Alright, so here we go. Alright, so first I'm going to check the common point, which is PP bus, 12 volts. This fuse. Oh, we have a short. Huh, just like that. There's a short on PP bus. As you can see, that's a dead short there. Right, most of the times, maybe one of the audio amplifiers are broken, or it can be one of these tantalum solid capacitors, or it can also be a broken DR MOS, right? So most of the times, those are the faulty components causing the PP bus to be shorted in it. Alright, so first I'm going to head over the thermal camera. Right, I'm getting over to the thermal camera. So I'm going to inject some voltages, right? So I'm going to run a jumper wire here at the fuse here at the PP bus, common point. Yeah. Alright, so alright, so I'm going to run the wire. On the common point, on the fuse there. Right, so I'm going to head over to the camera. Alright, so as you can see now I'm on the camera. Alright, so first I'm going to check in the audio amplifier section. So the audio amplifier section is right here. Right, this is the audio amplifier section here, right in this section here. Right, so I'm going to go into the thermal view. Right, so I'm going to seek, and I'm going to give power. All right, after 2, 1, 2. All right, let me see what happened. If I'm getting, all right, let me go again. I'm injecting roughly 5 volts currently now. Okay, so I'm back. All right, so I was the wiring wasn't correct. I wasn't getting proper grounding. All right, so I'm going to give power. Let's see if I see there's a heat coming from the CPU side. Let me reseek again. Oh, so we have a broken CPU and a DR MOS. So My DR MOS is broken. This one is broken, so the CPU is dead. Okay. All right, going under the microscope. So this one, it's getting hot, so I'm going to remove it. All right, so the DR MOS is removed. So I'm going back to the PP bus fuse, and I will check on the fuse. As you can see, the short is now gone, so the CPU is most likely dead. I'm going to replace it and give power and see, but I know the CPUs are most likely dead. This is a SRE-Z2, sorry, and this should be a 10th gen, I think. I'd have to confirm. Let me check the CPU core coil. I get 001000, so that indicates to me it's coming back to 1 now. 0. Alright, so that indicates to me that the CPU is most likely is dead. As you can see, the other core 000, right? The graphics 2, the graphics section is good, but the core section is burnt. 000. So the CPU will most likely have to be replaced if I can find it. So I'm going to put back another DR MOS here. So I'm just here tuning the pads. Alright, so I need a DRMOS. Alright, so I have a donor here. I'll take this one. Right. I'm gonna solder the new one now. Alright, so adding some flux. There we go, so it's now snapped in place. There we go. Cleaning up the excess solder from the edge. Alright, so I'm cleaning now. Alright, so I will measure so the CPU, it will turn on, but there will be no display. Alright, so the resistance is 1. Alright, so it will turn on, but it will not display, so I'm going to give power now. Alright, so I'm going to give power. Alright, so as you can see, it's now 5 volts and it's boosting to 19 volts. As you can see, the current there is 100, 170, 100, 200, 200, 600. What? Could that be that the CPU is working? Is that a fix? 99% of the time, if the DRMOS is broken, then the CPU got hit by that 19 volts with that high current, and you have to replace the CPU as well. So could that be that it's working? The current that I just got is about 700 going to 800 milliamp. Could that be that the CPU is saved? Let's see. Alright, so I'm going to just connect the display. I'm going to connect the the board into the chassis here because I'm curious. I don't think the CPU is working. The current looks good, to be sure, but I just want to see what's going on. Oh, I didn't connect the heatsink. Okay, so the board is inside. Alright, so I'm giving power. What the? You see that? The CPU is alive. I get Apple. What the? How is that even possible? Well, it's possible because it's a micro short, right? So what happened is that during the working process of the CPU power supply, right? Each power supply coil on the CPU, so it's two phases, right? So it's two phases, right? And one, so 2 plus 1, which 1 for VCC SA and 2 for the CPU core. When the CPU core is actually in the process of working, the CPU needs to get a certain amount of current. So each coil have what is called shared current, right? Because the coil, as I said before in another video, is a blind person. It's an unreliable component. It cannot manipulate or to understand current switching and current changing between the front end and the back end of the coil, because a coil just basically produces voltage and high current and stores it as an electrical charge and release it as an electrical charge at the same time. So each time the front end and the back end of the coil gets voltage, the back end discharge and charges, charge, discharge, charges, discharge, charges, discharge, charges. So after a period of time of that constant charging and discharging, it builds up that high current, and then it stores it with the magnetic wound that is wrapped inside of the core of the inductor, and it slowly releases it as electrical charge and produce stable, clean DC voltage, right? So that is why it says that a coil basically acts as a filter, and it blocks high frequency and pass low frequency. So during the working process, when the MOSFETs are switching, right, the CPU power supply chip needs to get the information about that amount of current that is generated on that coil, right? So any coil on the CPU core supply is not producing enough current and voltage for the CPU to meet the CPU power demands. What will happen is that the MOSFET will constantly switch and it's run hot, and then it breaks because there's no compensation, right? The CPU power supply chip not compensating for the amount of heat, current or temperature which is done by the switching frequency of the CPU power supply chip. And then after that fast switching, it runs hot and switch too fast because what? It's not dropping the frequency switching. So the CPU MOSFET inside the CPU core power supply will constantly switch, and then it will just break, and the 19 volts will just enter into the CPU and break in the CPU, right? So this is what normally happen on a typical CPU power supply core. When the core supply is shorted, the MOSFET is broken because it's not compensating for the current and the temperature, right? Remember, so the CPU power supply is all about current compensation, temperature compensation, and impedance, right? So this is why for the Apple they normally put a resistor, sorry, let me go under the microscope. So they normally put a resistor at the end of the coil here for current compensation. Here it is. So we have one resistor here, we have another one here, right? We have one more here, as you can see. So at the back end of the coil, which is here, this is the back end of the coil, right? There's a current sensing resistor, so it needs to sense the amount of current that is generated, so there's no current loss, right? And it is producing the right amount of current so they don't burn the coils. The coils sometimes changes color because it is not compensating, and if there's a short on the rail, or a micro short on the rail, then it will run too hot. So that is why they have to put a varistor, this component. So these components, as you can see, they are let me see if I can find it. It's normally close here. This is a varistor. This is monitoring the temperature of the coil, right? So each coil needs a set of varistors. So maybe this one is under the other side of the board for this one. I'm not seeing this one, but you can see this is one for this phase. All right. I'm not the other one for the others are under the coil. Let me see here. As you can see, there's another one here, right? This is monitoring the temperature, right? So this is one. So this is a thermistor, or we can call it a varistor. Where is the tweezer? Oh, sorry. So this is a sorry. Yes, this is a thermistor, or we can call it a varistor. So when the temperature increases on the coil here, the resistance decreases. When the resistance decreases, it's going to tell this CPU power supply chip to drop the switching frequency so that it don't burn the MOSFET, because the MOSFET is going to switch too fast, and when it switches too fast, it gets hotter and hotter, and there's no compensation for the temperature. So this is why they put a resistor here to monitor the current. That's too much. If too much current is generated on this line, the total amount of current that is generated from the back end and the front end of this coil is going to report back to the CPU power supply chip to tell it that too much current is being produced, or too low of a current. Increase the current by increasing the duty cycle for the switching of the DR MOS, right? Because there are two MOSFETs that are inside of the CPU power supply chip. Yeah. Sorry about that. Right, so that is the working order. So each coil needs to produce a shared current, and that shared current is grouped together and sent as a total amount of current to the CPU power supply chip, so it can constantly monitor the current on the CPU power supply. Because the CPU needs so much current, this circuit needs to meet the demands of the CPU, right, to produce the proper voltage and current during the working process. So the voltage is always fluctuating on the CPU core, right, because it's a dynamic output of voltage. It's not a fixed voltage, right? So I'm going to assemble the unit now and then do a final test and get back to you. Okay, so I decided to show you. All right, so I'm going over to the schematic to give you a breakdown of what I was explaining, to see if it can be a bit more clearer. All right, so these are the DR MOS. As you can see, we have V in, and it's a FDMF 580908A, right? And as you can see here, we have the main power supply, which is VCC, which is 5 volts. We have V in, and we have VCCM, FCC, right? Constant current mode, which is a mode that is used to control by the switching of the internal MOSFETs, right? We have PWM, which is the main as an enable pin for this DR MOS. We have A ground and we have P ground. So the analog ground is the ground for this chip. The P ground is the ground for the lower MOSFET. This V in is for the upper MOSFET drain pin, and this is the lower MOSFET source pin, which is connected to the ground, right? Then we have the output switching, and we have the boot, which is going to basically boot the upper MOSFET gate, right, from 12 volts to 17 or 20 volts. This is from there. This is 12 volts, so 12 plus the 5 volts, right? So this 5 volts is coming in as working voltage. We have PVCC, which is going to the internal diode inside of this DR MOS, which is going to switch. So let me get the pointer fix. All right, so we have one MOSFET here, and we have another MOSFET here, right? So there are two MOSFETs. So one is connected to the ground here, and this is the drain pin is connected to the 19 volts, right? So as you can see, this is coming to this. This is the upper MOSFET, and this is the lower MOSFET, and this is going to output to the switch pin here, right? So as you can see, the two switches, it's going to output the CPU core. Now the gate So the gate is controlled by the PWM, right? Both gates are controlled by PWM. So there's a lot of pulses here, right? So we normally use an oscilloscope to check on this pin, right? And it will output based on the duty cycle, determines the amount of voltage, right? The larger the duty cycle, the larger the voltage, hence the larger the current, right? So this is the core supply, as you can see. Switch, and it's going to output core switch 1 voltage, right? So during the working process, these MOSFETs are working internally inside of this DRMOS, right? And they switch and they produce a pulse here, right? So that pulse is going to go to this coil, which is the front end of this coil, right? So as you can see, between this resistor here, this is the current sensing resistor that I was showing you. So this is saying CPU core I sense. I stands for current sense 1 positive, right? This is the first core, right? That is called PH1, right? The other one should be 2. As you can see, I sense 2, right? This is CPU core PH2, right? And so on and so forth, and then 3, right? This is VCC SA, right? So there's 2 core and the system agent. SA stands for system agent, right? So this is the CPU core 1 and PH 1 and 2, right? So this is the current sensing resistor. For the Apple, they don't use the coil as a way of to monitor the current, because this is a blind man, it's unreliable. But for the ordinary computers, they normally use it for current monitoring and impedance. Now, so they use this resistor now, as you can see, to calculate the voltage difference from pin number 2 and pin number 1, which is negative and positive, right? So as you can see, we have a set of resistors here, which is going to monitor the current, right, to calculate the current difference and send it back to the CPU core supply to tell it the amount of sum of the current, right? The total current that is generated on this rail. It needs to be monitored by the CPU power supply chip so it can sense it. If there's too much current generated here, right, what will happen is that it will go back. This is the CPU power supply chip, as you can see, ISL 95, A28, right, U7100, and it will come to this pin here, as you can see, right? For B, this is for the B side, and we have the A side, right? And we have the C side. So if whatever is generated here, the total amount of current which is generated, right, on the positive and the negative side, right, there's an internal amperial amplifier that's inside, right? So it is connected to one side, and the other side is connected to the non-inverting side and the inverting side. So what will happen is that if there is too much current, it will basically connected to these compensation resistors and capacitors, and this is basically used to correct the output error of the output voltage, right? So any error that is is generated on this part, this CPU core is going to be compensated for the amount of voltage and current, right? Right, so as you can see here, this part is also coming to here, which is the current monitoring of the B side. All the current that is generated from the sum, the total amount of current, is going to come to pin number 2 here to tell the CPU power to drop the switching frequency of the CPU core supply so you don't burn the MOSFETs, right? So that is the order. I don't want to go too deep because this is a very complex circuit, right? If you want to learn more about the circuit, you can direct contact me, and I will give you a breakdown at a fee, because many guys who repair CPU motherboards doesn't know how the CPU core supply works, right? So if you want a breakdown, I can give it to you, and you can contact me. All right, so I'm going to assemble the unit, and then I will get back to you after finish. Okay, so I will now just testing to see if the battery is charged. All right, so I'm getting some current there. It's booting up. I like that sound. That sound, I call it assurance. The charm, or you can call it the darm. Ah, there we go. Beautiful. So the repair is successful. So the CPU was saved. As you can see there, the CPU is saved by that microshort there. That MOSFET didn't fully break to hit it with the 19 volts. Or 12 volts rather for the MacBook. Alright, so I hope you enjoyed the video. I hope you like, subscribe as usual. And tomorrow should be a live stream for me. So I'll see you tomorrow in the live stream.